Good evening, everybody. A pretty bizarre problem. I sort of made this one up. It was motivated by another problem I saw in a math competition. I can't quite remember if it was AIM or SMO. I'm not sure. But when I first saw this in that competition, I thought, what do you mean? It looks nothing like an infinite geometric series, and it's interpreting. And I modified the instructions slightly. But those of you familiar with an infinite geometric series know that as long as you have a common ratio, this R is what they call the common ratio, and as long as that common ratio is between -1 and 1, and you can write that like this, the absolute value of R is less than 1, and that's tantamount to saying -1 is less than R is less than 1 when you strip away the absolute value bars. And this formula actually comes from a finite geometric series where as you elevate R to higher and higher in powers, it gets closer and closer to zero. And so that's why this thing ends up being a simpler looking version of the finite geometric series. Now, F, of course, stands for the first term, okay? And, of course, R is the common ratio. And you see you just multiply by higher and higher powers of R. So that should motivate you to make this quotient, this complex quotient, if you want to call it that, look like this, and then you'll know what the infinite geometric series looks like, and you'll be able to answer the question in a fairly direct fashion. Now, so I do that right down here. If you'll notice, folks, what I did, you need a 1 in this position, so I divided top and bottom by 1 over 350, 1 over 3 to the 50th power, excuse me. You can think of it as multiplying top and bottom or dividing by 3 to the 50th, however you want to think about it. In any event, what you're doing is you're multiplying this expression by a cleverly disguised version of 1, okay, which doesn't change it numerically, right? It changes its appearance. But y'all notice when I do this, this is 1 over 350, 1 over 350, top and bottom. And you get the 1 right here, which is important in terms of interpreting this thing as a geometric series. All right. Now, a little bit of algebraic manipulations right here. Common denominator in particular will make this circle object be equal to the first term in the series. And so I'll just call that F. All right. And then, of course, we have a common ratio that's a lot less than 1. 1 over 3 is might as well be 0, right? Okay, so this circle object right here is going to be equal to our R. Okay? So you see, we have everything from this nice, very clean, fairly famous formula here. We know what the first term is, and we know how to get the other terms by multiplying through by higher powers of R. So that's what happened here. Here's the first term, right? And again, we're looking for the first term that is less than 1. The first term that is less than 1. Well, this first term is certainly much greater than 1. And notice how right here, you can see I read this out so you could see just an example here if you're not seeing how this is working. 1 over, what do we got? 3 to the 30th quantity squared is 1 over 3 to the 60th. Right? So you see this is going to have the effect of deflating the numerator, so to speak. You see, so this one is clearly greater than 1. This one is still greater than 1. You see, when you multiply right here, you would have 3 to the 80th. This is still going to be greater than 1. When you multiply through by 3 to the 60, you're still going to be greater than 1, right? And it's getting kind of close. Right here you have 90 and 50s, 3 to the 140th, but this one's still greater than 1, right? So let's keep going. Oh yeah, it looks like I ran out of space here. Now, but notice right here, this part right here is clearly less than 1. That's because you would have the effect of 3 to 1/70th, 3 raised to the 1/70th power, which is going to wipe this out, right? And so this would be the very first term that is less than 1. And I'm not going to go to the trouble to simplify that. That's the term right there. And that term is clearly less than 1. So the first, this would be, look, what is this? 1, we have the first term here. This is the first term, the second term, the third term, the fourth term. So this is the fifth term, if you prefer to answer the question that way. That would be the fifth term. The fifth term in the series, again, 1, let me count again, 1, 2, 3, 4, and this is the fifth term, right? So the answer to the question is definitely the fifth term. The fifth term is the first term. That's a little confusing, isn't it? The fifth term is the first term that is less than 1. And y'all, let me know what you think about this ilk of problems. I kind of like it, you know, because at first when you read this, unless you're familiar with this, and most people have sat through a calculus class or an analysis class like Baby Rudin or any of those courses that teach real analysis or calculus. I don't know, sometimes calculus in the U.S. doesn't emphasize this as much as it probably should, but definitely in a real analysis course, you'll learn this stuff. And when you look at this, you go, wait a minute, this looks like it's a million miles from this nice expression here. And it isn't, though. If you focus on this term becoming a 1, it all works out. And it's useful at this stage right here to write this as a single fraction, although you could leave it like this, and it's a little clunky to carry it around that way. But we get our first term, we have a very conspicuous common ratio, and then it's easy to construct the series, the infinite series, and determine which of the terms meets the conditions of the problem. But anyway, again, what I got was the fifth term, and that's all I have for tonight.